Now then, we move on to the final part of geometric sequences and series. So far we've found our common ratio r, we've calculated the nth term using a, the first term, times r to the n minus 1, we've found the sum of a geometric sequence or series, and we've solved problems involving growth and decay, interest and depreciation. Today's lesson we're going to find that there are certain sequences where we can actually find the sum to infinity, that is, we can find the sum of the complete sequence. Okay, and you'll find there's some special things. So please remember we've got these formulae we given, okay, and we're going to learn in this lesson how we use this one down the bottom here. So how we use this formula here. We're going to use this and find where we derive it from. First of all, a little bit of background. If we consider this sequence here, so 3 plus 1.5 plus a quarter plus 0.375, okay, what we got, the first term is a, and the common ratio is a half. Okay, so if we think about what the sum to the nth term is going to be, we're going to put in a equals 3, r equals a half, and we're going to get this equation. Now notice here I've got the version with 1 minus r to the n on the top, 1 minus r on the bottom, so it's positive. Okay, both bits are positive. And we can simplify this and we get this equation here. Now if we put in certain values, put in n equals 3, we get the value 5.25, n equals 5, 5.8125, and so on, up to n equals 20, 5.99994. And we find this value here, the sum, is getting closer and closer to 6. It seems it's never going to either reach it or exceed it, so it converges on 6. One of the properties about this is the value of r is between -1 and 1. It's not equal to them, it's between those two values. And when it is between those two values, we'll be able to find the sum to infinity. And the reason behind this, if we take our formula for Sn and substitute a value in between -1 and 1 for r, we find that this value r to the n, it tends to 0 as n tends to infinity. If we do, say, for example, a half to the million, it's a very, very, very small number, so it vanishes. So in fact, when we put it in here, this value, r to the n, actually equals 0 if n is infinity. So the top of the fraction simply becomes a. So we find we get the sum to infinity is a over 1 minus r. But the crucial thing is, r must be between -1 and 1. That is, the modulus, the size, the positive value of r, must be less than 1. Okay, if you need to remember that, that means that. Okay, so the modulus of r is -1, less than r, less than 1. So, let's go and do some mathematics with this. So for the first example here, okay, if we start up here, we got a is, well, the first term is 40. The common ratio is a quarter. Well, we're simply substituting in. The sum to infinity is a over 1 minus r. Now when we substitute this in, okay, we've got 40 over 3/4, which means we're going to get 160 over 3. It's easiest to leave it in that form. In fact, if you type it into your calculator, if you type the first bit in, type this in, it will leave it in this form. Okay, it may give it to you as a mixed number, it doesn't matter. Okay, now if we look at the next one, okay, what we're given here, that a equals 1, and if you think, what do we multiply by each time? We're multiplying by 1 over p. We can find this, of course, by just doing r equals one term over the other term. So it's 1 over p. So we're substituting in. The sum to infinity is a 1 over 1 minus 1 over p. Now here we're going to have to manipulate this. If we multiply both top and bottom by p, okay, then we're going to have p on the top, we're going to have p times 1 is p, and p times this over here, which is going to be -1. And so that's our answer. Okay, we find that, of course, remember, multiply 1 by p, we get p, multiply 1 by p, we get that there, multiply 1 over p by p, and we get -1. So, they've got to make this a bit more challenging. It's a very simple formula to use. So here's an example. We're told that the sum to 4 terms is 15, but the sum to infinity is 16. So if we think we're going to get 2 equations from this, okay, so first of all we're asked to find the possible values of r. Well, if we put it into the first one, the sum to the first 4 terms is 15. Well, 15 therefore is the first term, which is a brackets 1 minus r to the 4 over 1 minus r. But at the same time, we know the sum to infinity, which is 16, must be a over 1 minus r. Now if we look carefully here, can you see we've got a over 1 minus r? We know a over 1 minus r is 16. So in fact, we can substitute this in. So what I've done there, a over 1 minus r is here, which we know is 16. So I've just taken off that and replaced it with that. So if we rearrange this, we get 15 over 16 is 1 minus r to the 4. Well, rearranging, if I bring the r to the 4, if I take the r to the 4 over this side, it makes it positive, and if I subtract 15 over 16, what I'm left with is r to the 4 equals 1 over 16. So in fact we need to take the 4th root of 1 over 16, which means that r is plus or minus 1/2. Okay, you can do that on your calculator just to check. So for part B, we're given that all the terms are positive. Well, if all the terms are positive, then r must be equal to 1/2, because if it was negative 1/2, then the term would go positive, negative, positive, negative. We also can find out the value of a. Okay, if we know that, well, we know 16 equals a over 1 minus r, then we can substitute in 16 equals a over 1 minus 1/2, which is 1/2, and rearranging this, we get a equals 8. Okay, all we've done is multiply both sides by 1/2, so you get 1/2 of 16 equals a. Now, you should be ready to go on to exercise 7e. Again, go on to the harder questions. Don't just look at the ones where it's a sequence given to you. The ones in the exam are more likely to be of the style from question 2 to 10. And then finally, have a little look at the mixed exercise. Now, if you get stuck on any questions, please don't hesitate to email me, and I'll do my best to feed back to you as soon as possible. Good luck.